Measurements. Centuries ago, people believed that stars were holes in a vast crystalline celestial sphere through which heavenly light shone. How large this sphere might be was unclear, but it was certainly enormous. Modern researchers can sympathize. From a practical standpoint, the distance to the stars seems infinite. When you drive down a road, nearby trees rush past, while distant mountains appear to move more slowly. The moon, being extremely far away, seems almost stationary compared to closer objects. Your brain might even trick you into thinking it closer and smaller, and that it's actually following you. It's a little strange. Sometimes people mistake it for a UFO trailing them. Measuring the distance to something incredibly remote is difficult. It's not as simple as pacing it out with your feet. Or is it? The ancient Greeks already knew Earth was round, and they had many ways to prove it. For instance, ships sailing over the horizon appeared to vanish from the bottom up, exactly what you'd expect if they were moving along Earth's curve. But how big was Earth? Over 2,000 years ago, the Greek philosopher Eratosthenes calculated its size. He knew that on the summer solstice at noon, sunlight shone straight down a well in Aswan, then called Syene. At the same time in Alexandria, the sun did not reach the bottom of a well, and he could measure the angle of that difference. Legend has it he paid someone to walk the distance between the two cities to measure it, but more likely, he used data from earlier surveying expeditions. Either way, knowing both the distance and the angle, and applying a bit of geometry, he calculated Earth's circumference. His estimate, just over 40,000 kilometers, was astonishingly accurate. For the first time, humanity had measured the scale of our planet. That first step launched a much longer journey. Once you know Earth's size, you can determine other measurements. During a lunar eclipse, Earth's shadow falls across the moon. You can see the curvature of Earth's edge as the shadow moves. Knowing Earth's size and applying some geometry lets you calculate the distance from Earth to the moon. Moreover, the moon's phases depend on the angles and distances among Earth, the moon, and the sun. Using Earth's size as a starting point, Aristarchus of Samos calculated the distances to the moon and the sun, and their actual sizes, over 2,200 years ago. His numbers weren't precise, but that wasn't the point. His methods were sound. Later, great thinkers like Hipparchus and Ptolemy refined these techniques to produce far more accurate measurements, all more than 1,000 years before the telescope was invented. This convincingly shows that these early astronomers were already grasping a solar system millions of kilometers across. But at this point, things grew complicated. Planets are so distant they appear as mere points of light, and the measurement methods of the time couldn't yet reach them. In the 17th century, Johannes Kepler and Isaac Newton laid the mathematical foundations for planetary orbits. This theoretically made calculating planetary distances easier, but there was a catch. Such calculations revealed that measuring distances to other planets required precise knowledge of the Earth-Sun distance. For example, it was known that Jupiter orbits about 5 times farther from the Sun than Earth does. But that didn't tell us the distance in kilometers. How far is the Sun, really? They had rough estimates based on Greek figures, but to truly understand the solar system, they needed greater precision. To emphasize the importance of the Earth-Sun distance, astronomers gave it a special name, the astronomical unit, or AU. Note its unit, not units, highlighting how fundamental it is to all cosmic measurement. Many methods were tried. Occasionally, Mercury or Venus would transit across the Sun's disk. By precisely timing these events from different locations on Earth, scientists could plug the data into orbital equations to pin down the AU's exact length. Massive global expeditions were launched for this purpose, and their results were decent. But Earth's atmosphere blurred planetary images, introducing significant timing errors. The best they could say was that 1 AU equaled 148.51 million kilometers, with an uncertainty of 800,000 kilometers. Good, but not good enough for astronomers. Finally, in 1960, astronomers used a radio telescope to bounce radio waves off Venus. Since the speed of light is known with extraordinary precision, the round-trip travel time of those signals could be measured with stunning accuracy. After centuries of effort, the astronomical unit was finally pinned down: 149,597,870.7 kilometers, the average distance from Earth to the Sun, accounting for Earth's elliptical orbit. Determining the Earth-Sun distance became the cornerstone for unlocking the secrets of the solar system. This number is astronomy's fundamental ruler, the baseline against which all other cosmic scales are measured. Understanding it allows us to predict the motions of planets, moons, comets, and asteroids. It also enables us to launch spacecraft, explore distant worlds up close, and deeply understand the nature of our cosmic neighborhood. Even more remarkably, defining the AU played a crucial role in measuring distances to the stars. Humans have binocular vision. Our two eyes see the world from slightly different angles. When we look at a nearby object, the left eye sees it from one perspective, the right eye from another. The brain merges these images, compares them, and, through a complex geometric calculation, creates a sense of depth. So yes, that school math really does come in handy. This ability is called depth perception. You can easily demonstrate it with your thumb. Close one eye, then the other, and your thumb appears to shift against the background. This effect is known as parallax. Its magnitude is directly proportional to the distance between your eyes, the baseline, and inversely proportional to the object's distance. Knowing your inter-eye distance, you can use trigonometry to calculate how far away something is. Close objects show large shifts, distant ones, tiny shifts. But this method only works within the limited range of human vision. Stars are far beyond that. To measure stellar distances via parallax, you need a baseline far larger than a few centimeters. Once astronomers accepted that Earth orbits the Sun, not the other way around, they realized Earth's orbit itself could serve as a massive baseline. Observe a star when Earth is at one point in its orbit, then again 6 months later when Earth is on the opposite side. In theory, you can measure the star's parallax, and thus its distance, provided you know the size of Earth's orbit. That's why the astronomical unit is so vital. Earth's orbital diameter is about 300 million kilometers, making it an excellent baseline. Yet, for centuries, no stellar parallax was detected. Did this disprove the heliocentric model? No. The stars were simply too distant, their parallax too tiny to measure with early instruments. The first successful measurement came in 1838 for the star 61 Cygni. Though faint, it was close enough for astronomers to detect its subtle shift as Earth orbited the Sun. 61 Cygni lies about 720,000 AU away, over 100 trillion kilometers. That distance is so vast that the AU becomes impractical as a unit. Astronomers adopted a new unit, the light year, the distance light travels in 1 year. Light moves at about 10 trillion kilometers per year. While enormous, this unit makes cosmic distances more comprehensible. Thus, we say 61 Cygni is 11.4 light-years away. Astronomers also use the parsec, based on parallax. A star with a parallax of 1 arcsecond, 1,003,600 of a degree, is 1 parsec away, equivalent to 3.26 light-years. Convenient for professionals, less so for interstellar travelers. The closest known star to the Sun, Proxima Centauri, is about 4.2 light-years away. The farthest stars visible to the naked eye lie over 1,000 light-years distant, though most are within 100 light-years. Today, space-based satellites precisely measure distances to hundreds of thousands of stars, but only out to about 1,000 light-years. Still, these nearby measurements provide a foundation for gauging more remote stars. How? Like gravity, light's intensity follows an inverse square law. If 2 stars emit the same amount of energy, but one is twice as far away, it appears 4 times dimmer. 10 times farther? 100 times dimmer. So, once we know the distance to a nearby star via parallax, we can compare its brightness to a more distant star of the same type to estimate that star's distance. The key is confirming they're the same kind of star. Some stars are intrinsically brighter, but spectroscopy reveals their true nature. In fact, a star's distance is the key to understanding nearly everything about it. Once we know how far away it is and how bright it appears, we can calculate its true luminosity, how much light it actually emits. Its spectrum tells us its temperature, and from that, we can infer its mass, size, and more. When humanity finally grasped the distances to the stars, their true physical nature was revealed. That knowledge, in turn, sparked the development of even more powerful distance-measuring techniques. Light from dying, exploding, or pulsating stars, whose brightness varies predictably, serves as reliable cosmic yardsticks. These and other phenomena now let us measure the trillions of kilometers separating us from distant galaxies. By observing stars in other galaxies, we can even determine the true scale and size of the entire universe. And it all began with the curious minds of ancient Greeks, whose simple question, "How big is Earth?" ignited a chain of discovery that continues to this day. Curiosity, it turns out, is the engine of progress, capable of leading us to the most astonishing revelations. In this episode, we've seen how the ancient Greeks measured Earth's size, used that to calculate distances to the Moon and Sun, and later, once the astronomical unit was known, applied parallax to reach the nearest stars. That breakthrough became the foundation for using stellar brightness as a tool to measure even greater cosmic distances. Crash Course Astronomy is produced in collaboration with PBS Digital Studios. Be sure to subscribe to their YouTube channel for more amazing content. This episode was written by Phil Plait, edited by Blake DiPastino, and Dr. Michelle Thaller served as scientific consultant. Directed by Nicholas Jenkins, edited by Nicole Sweeney, sound design by Michael Aranda, and graphics by Thought Cafe.